Yogah Karmasu Kaushalam.
Hello, I Anita Gharekhan from Siusha Science College, Ahmedabad. Thank UGC Human Resource Development Center of Gujarat University for giving me an opportunity to connect with you and deliver my session on spectroscopy. I thank Professor Dr. Jagdish Joshi, Director of UGC HRDC of Gujarat University. Under his guidance and supervision, the first of its kind online annual refresher program in English language teaching, that is ARPIT, with record break 9,000 participants in the year 2019-2020 was organized. HRDC Gujarat University even coordinated the online e-content creation training for all the professors of the colleges and universities of Gujarat, along with Department of Higher Education, Commissionerate of Higher Education and Knowledge Consortium of Gujarat in the same year, that is 2020. I also thank Professor Dr. P. N. Gajjar and Associate Professor Dr. Aditya Vora of Physics Department, Gujarat University, coordinators of second online refresher course in Physics 2022. Far from its source, an electromagnetic radiation consists of waves of oscillating electric and magnetic fields, that is electromagnetic field, propagating through space at speed of light, that is 3 lakhs km per second, and carrying electromagnetic radiant energy. Electric field and magnetic field are mutually perpendicular to each other. Electric field is in the y direction, magnetic field is in the z direction, and both of these propagating in x direction perpendicular to both electric and magnetic field. Electromagnetic radiation includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. All of these waves form part of the electromagnetic spectrum. The electromagnetic spectrum is the range of frequencies of electromagnetic radiation and their respective wavelengths and photon energy. The electromagnetic spectrum covers electromagnetic waves with frequencies ranging from below 1 Hz to above 10 raised to 25 Hz, corresponding to wavelengths from thousands of kilometers down to a fraction of the size of an atomic nucleus. This frequency range is divided into separate bands, and the electromagnetic waves within each frequency band are called by different names. Beginning at the low frequency, that is long wavelength end of the spectrum, these are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays at the high frequency or short wavelength end. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. Gamma rays and X-rays overlap in electromagnetic spectrum, which can make it hard to differentiate them. Now we can see something like that. Wavelengths we can compare with whatever we saw around us. wavelength 10 raised to 2 meters, it is just like equal to a saucer field. 10 raised to 1, that is the size of a house. 10 raised to minus 1, that is the size of a baseball, and like so. Cell, then bacteria, virus, protein, water molecule, and comes to the atom levels. Now, some sources of these all the waves are given below for our idea. Radio waves, amplitude modulation radio, radio frequency cavity, FM radio, then microwave, from microwave oven, radar also produce microwaves. Our body produce somewhat infrared. Then comes light bulb and definitely sun, that is visible light. Then astronomical source is for soft X-rays. X-ray machines, hard X-rays, and radioactive elements produce gamma rays. As we can see, the visible light contribute a very small portion to the electromagnetic spectrum. Visible light spectrum is in between infrared and ultraviolet. In nanometer, its wavelength range is from 700 to 400. Electromagnetic waves are typically described by any of the three physical properties: frequency, wavelength, or photon energy. When any atom comes to ground state from an excited state, it releases photon, and the energy of photon is directly proportional to the wave frequency. We know C is equal to lambda nu. In wave number, nu bar is equal to 1 upon lambda. Nu bar is the wave number. We know energy is given by h nu. Now replacing nu by C upon lambda, and in wave number energy is equal to hc nu bar. This is for one photon. For number of the photons, below will be the formula. From here we can see when any atom goes to higher state, then it can't stay there, it has to come back to the lower energy state, and that h nu, that is the energy, is a difference between the excited state to the ground state. So h nu is equal to E2 minus E1, and the wavelength can be given by this red arrow. Again coming back to the electromagnetic spectrum, we have seen energy is directly proportional to the frequency. So we can say gamma rays, which are at the higher end range, it is having highest energy, that is greater than 10 raised to 4 electron volt per photon. The shortest wavelength, that is the less than minus 14 meters, and the highest frequencies typically more than 10 raised to 19 hertz. On the other hand, radio waves have the lowest energy, that is in the femto electron volt. Longest wavelength from thousands of meter to 30 centimeters, and lowest frequency of course of any type of electromagnetic radiation, that is 3 kilohertz up to 300 gigahertz. Photonics, as the name says, it is the study of photons. Now what is photonics? Photonics is the physical science and application of light generation, detection, manipulation or controlling through emission, transmission, modulation, signal processing, switching, application and sensing of light. As we all know, light has a dual nature known as wave-particle duality. That is to say that light has characteristics of both a continuous electromagnetic wave and a particle that is photon. Photonics plays an important role in driving innovation across an increasing number of fields. The application of photonics spreads across several sectors from optical data communications to imaging, lighting and displays to the manufacturing sector to life sciences, healthcare, security and safety. Some names are given below: light detection, telecommunication, information processing, illumination, meteorology, spectroscopy, holography, medicine, which includes surgery, vision correction, endoscopy, health monitoring, etc. Military technology, laser material processing, visual art, biophotonics, agriculture and robotics, and more. Though most photonic applications are in the visible and near infrared spectrum, but it also extends to the ultraviolet, that is 0.2 to 2.35 micrometer wavelength. Then long wave infrared wavelength is from 8 to 12 micrometer, and far infrared portion of the spectrum, that is 75 to 150 micrometer wavelength. What is matter? A matter is referred to a substance which has a certain mass and takes up certain volume in space. For example, pen, pencil, toothbrush, water, milk, all are matters, as well as car, bus, bicycle, air, sugar, hydrogen, oxygen, etc. all are matter. Matter can be perceived by our senses. Everything in universe except energy is made up of matter. So matter is considered as a living thing as well as a non-living thing. Human body is made up of matter and energy. In detail, matter is made up of atoms and molecules, or we can say anything made of positively protons, neutral neutrons and negatively charged electrons is called matter. It is considered matter has 7 states: solid, liquid, gas, ionized plasma, quark-gluon plasma, Bose-Einstein condensate and fermionic condensate. But matter on earth is in the form of solid, liquid or gas. Gas, total disorder of particles, much empty space. Particles have complete freedom of motion. Particles are apart. Liquid, in liquid disorder is there. Particles or cluster of particles are free to move relative to each other, but they are close together. Solid, ordered arrangement. Particles are essentially in fixed position. They are close together. By cooling or heating, by compression or reduced pressure, all the states of matter can be interchanged. We have seen the characteristics of light and matters. Now, question is how light interacts with matter. When light interacts with matter, it can do one of the several things depending on its wavelength and what kind of matter it encounters. It can be transmitted, it can be reflected, it can be refracted, it can be diffracted, it can be polarized, it can be absorbed, or it can be scattered. Mirror. Mirror reflects light in a particular direction. Movie screen scatters light in all directions. Movie screen scatters light in all directions so that every person in the audience sees light from all parts of the screen. So the interaction between light and matter determine the appearance of everything around us. Here in this picture, the sun and the lamp are the sources of light, which emit light in all the directions. The mirror reflects all colors of the visible light. The chair is red because it scatters red light and absorbs all other colors. Spatial cells in the eye absorbs light, leading to vision. The snow absorbs some light, which aids melting, but scatters most light, so it looks bright. The glass transmits all colors of visible light, so it looks transparent. The tree is green because it scatters green light and absorbs all other colors. Spectroscopy. Spectroscopy is the general field of study that measures and interprets the electromagnetic spectra that result from the interaction electromagnetic radiation and matter as a function of wavelength or frequency of the radiation. When light falls onto an atom, the oscillation of electromagnetic wave cause the electron to oscillate. In this fashion, the atom absorbs the energy of the light. If this atom now interacts with other atoms, it can pass along the photon energy that becomes a wave oscillation. In other words, spectroscopy is the study of absorption and emission of light and other radiation by matter. It involves the splitting of light, or more precisely electromagnetic radiation, into its constituent wavelength, that is a spectrum, which is done in much the same way as a prism splits light into a rainbow of colors. The basic principle shared by all spectroscopic technique is to shine a beam of electromagnetic radiation onto a sample and observe how it responds to such a stimulus. The response is usually recorded as a function of radiation wavelength. Most of what we know about the universe comes from studying the interaction of light and matter, which makes spectroscopy a fundamental technique in understanding the world us. In very simple words, Seeing is spectroscopy. We perceive the world via the interaction of visible light with the light receptors in our eyes. The light is emitted from the sun or from other light sources. It is then reflected from or transmitted through the objects in our surroundings. In these processes, the color changes because some of the light is absorbed by the objects. How much and what spectral region are absorbed depends on the atoms and the molecules in these objects. The light not absorbed reaches our eyes. It carries the information of the molecular structure of our surroundings with it. In our eyes, its color is analyzed by 3 different types of photoreceptors which absorb different light in spectral regions. In this same way, we perform a spectroscopic experiment every time we look at the things. There should be a light source and the objects that reflects, transmits, scatters and absorbs light and a wavelength dependent detector in our eyes. An apparatus for spectroscopic studies is called spectrometer, and a plot of a particular property of matter against wavelength, frequency or energy of radiation is called spectrum. Classification of spectroscopy. First is absorption spectroscopy. Uses the range of the electromagnetic spectra in which a substance absorbs. This includes atomic absorption spectroscopy, infrared spectroscopy and nuclear magnetic resonance that we call NMR spectroscopy in radio region, etc. Second is emission spectroscopy. The substance first must absorb energy from a variety of source and then emits. Third is scattering spectroscopy that measures the amount of light that a substance scatters at certain wavelengths, incident angles and polarization angles. One of the most useful application of light scattering spectroscopy is Raman spectroscopy. The scattering process is much faster than the absorption or emission process. Some common types of spectroscopies name are here: absorption spectroscopy, fluorescence spectroscopy, X-ray spectroscopy, flame spectroscopy, visible spectroscopy, ultraviolet spectroscopy, infrared spectroscopy, Raman spectroscopy, nuclear magnetic resonance spectroscopy. The absorption of light may result in a number of phenomena and can be explained with the help of Jablonski diagram. It is a powerful tool for visualizing the possible transitions that can occur after a molecule has been photoexcited. In this, first, what are the energy levels we should understand? The energy levels of a molecule are shown by horizontal black lines with energy increasing along with vertical axis. From here to here, energy is increasing. The bold line, this, here, here. Bold lines represents the lowest vibrational level of each electronic state. These are the electronic states. Here S0, S1, S2, T1 all are the electronic states. With the higher vibrational levels represents by thinner lines. The vibrational levels become more closely spaced as energy increases and eventually form a continuum. For clarity, only a subset of these vibrational levels is represented on the diagram. We can see the black bold lines are becoming thinner on the vertical axis and going nearer to each other. The naming of electronic states is based on the spin angular momentum configuration of each state. First is singlet states, that is represented by or denoted by S. Here in this we can see S0, S1, S2 are the singlet states, and the triplet state, that is the total spin angular momentum of 1 by T. Here in this 3 singlet states, that is the S0, S1 and S2 are shown, whereas triplet states is only one, that is shown by T1. S0, where the ground state is written, is the singlet ground state of the molecule. S1 is the first excited singlet state and S2 is the second excited singlet state, and so on. And Sn is the nth excited singlet state, not shown in the diagram. T1 is the first excited triplet state and Tn is the nth excited triplet state, not represented in the figure. Here the transitions are of two types, that is the radiative and non-radiative transitions. The colored arrows, green color, red color, orange, aqua, blue, violet, represents the various transitions that can transfer energy between the molecular states and are split into radiative and non-radiative transitions. Radiative transitions are transitions between two molecular states where the energy difference is emitted or absorbed by photons and are represented by straight arrows, whereas non-radiative transitions are transitions between two molecular states without the absorption or emission of photons and are represented by undulating arrows. Absorption. A radiative transition from a lower to a higher electronic states of a molecule. The energy of the photon is converted to the internal energy of molecules. It absorbs the energy and it get excited and go to the excited state. So, a molecule is promoted from its ground state to a higher state by absorption of a photon, which is represented by the green arrows in figure. In which excited state it will go, that depends upon the which amount of the photon energy it has taken. It is the fastest transition occurring on a time scale of order of 10 raised to minus 15 seconds. At room temperature, the majority of molecules in a population will be in the lowest vibrational level of the ground state, that is the Boltzmann distribution, and absorption is therefore shown to start from this level only. Absorption of a photon promotes the molecule from S0 to one of the vibrational level of the singlets excited states, that is the S1, S2 and so on. Direct excitation to the triplet excited state, that is the T1, T2 is not possible due to conservation of angular momentum. What is vibrational relaxation? It is a non-radiative transition to a lower vibrational level within the same electronic state. As we can see, S2 and S1, one arrow is there, that is of the orange color, that is the bigger one. It was in the S2 electronic state, that is the excited state. It will not radiate and it will come from the S2 to S1. Same way, a small arrow in the S1 of the orange color shows it was one of the excited state in the S1, but it has to non-radiate and come to the zero level of S1. After a molecule has been promoted to an excited state by absorption, it is in the non-equilibrium state and will eventually dissipate the energy that it has gained and return to the ground state. The first way that energy is lost is through vibrational relaxation, as I have explained just now with the orange arrows, where excess vibrational energy is lost to the vibrational mode within either the same molecule, that is the intermolecular, or to the surrounding molecules, that is the intermolecular, until the lowest vibrational level of the electronic state is reached. So, we can see one arrow from the S2 to S1 at the lowest vibrational level, and in the S1 from the arrow, small arrow of orange, that from the excited level to it is coming to the lowest vibrational level, that is written as shown as the 0. This vibrational relaxations occurs on a rapid time scale of 10 raised to minus 12 to 10 raised to minus 10 seconds and outcompetes all other transitions. Here, internal conversion. We can see one orange arrow, that is the S2, between the S2 and the S1 states. It is coming from the lowest S2 state to the one of the excited state of S1. Now, this is called internal conversion, but it will again radiate. How? Again a small arrow we can see in S1 from the excited state to it is coming to the ground state of S1. So, internal conversion is a non-radiative transition between two electronic states of the same spin multiplicity. A molecule in a higher lying single late electronic state may also undergo internal conversion to a lower lying singlet electronic state, which is shown by the orange arrows. Internal conversion is immediately followed by vibrational relaxations to the lowest vibrational level of the electronic state. The rate of internal conversion is inversely proportional to the energy gap between the two electronic states. Internal conversion of the closely spaced higher lying singlet excited state, that is S3 to S2, S2 to S1, etc., will proceed rapidly on a time scale of 10 raised to minus 11 to 10 raised to minus 9 seconds. In contrast, the energy gap between the S1 and S0 is much wider, and internal conversion between these states occurs on a slower time scale and will be in competition with other transitions such as fluorescence and inter-system crossing. Now, what is fluorescence? This is a radiative transition. So, it is a radiative transition between two electronic states of same spin multiplicity. The emission of photons from the S1 to S0 radiative transition is known as fluorescence, which occurs on a time scale of 10 raised to minus 9 to 10 raised to minus 7 seconds, as is shown by the red arrows in figure. As a consequence of the rapid vibrational relaxation and internal conversions processes described above, the fluorescence occurs with some assumptions. From the lowest vibrational level of the first electronic excited singlet state to the singlet ground state, this energy loss prior to fluorescence is the physical origin of the famous Kasha's rule, which states that luminance may be fluorescence or phosphorescence, only occurs with appreciable yield from the lowest excited state of a given multiplicity. It is also responsible for the Stokes shift, where the fluorescence occurs at a longer wavelength than the absorption. Inter-system crossing. It is a non-radiative transition between two isoenergetic vibrational levels belonging to electronic state of different spin multiplicity, means S1 or S or T. So, it is an alternative transition to fluorescence, and internal conversions is inter-system crossing from the S1 to T1 state, which is shown by the aqua colored arrows. This transition is in principle forbidden due to conservation of spin angular momentum. However, spin orbit coupling between the spin angular momentum and the orbital angular momentum makes it weakly allowed. Inter-system crossing is in competition with the other S1D population transitions, that is the internal conversion and the fluorescence, and is too slow to be relevant for the majority of purely organic molecules. One method of increasing the inter-system crossing rate is the incorporation of heavy atoms into the molecule, which increases the spin orbit coupling strength. After inter-system crossing, the molecule will immediately undergo vibrational relaxations to the ground vibrational level of T1. Phosphorescence, a radiative transition between two electronic states of different spin multiplicity. The emission of photons from the T1 to S0 transition is known as phosphorescence. Similarly, to intersystem crossing, phosphorescence is in principle a forbidden transition but is weakly allowed through spin-orbit coupling. A consequence of being a forbidden transition is that the phosphorescence rate constant is very low, and phosphorescence therefore occurs on a much longer time scale than fluorescence, with typical phosphorescence lifetime being in the 10 raised to minus 6 to 10 raised to 1 seconds range. Delayed fluorescence. A third type of radiative transition known as delayed fluorescence is also possible. Delayed fluorescence occurs when a molecule is in the T1 state transitions to the S1 state, followed by a radiative transition to the S0, which results in an emission identical in wavelength to standard fluorescence but occurring on a longer time scale. The human body is a single structure, but it is made up of billions of smaller structures of four major kinds, that is the cells, tissues, organs and systems. An organ is an organization of several different kinds of tissues. So arranged that together they can perform a special functions. So when groups of cells do the same kind of work, they are called tissues. The human body is made up of all the living and non-living components that create the entire structure of human organism, including every living cell, tissues and organ. Now we have seen how light interacts with matter. Now human body is made up of matter, living and non-living. So definitely when light falls on the body, I am not talking about the full body, any organ, tissue, then what will happen? There will be a four interaction will occur, that is the reflection, transmission, scattering or absorption. It means we can able to study human body, any organ, any system, any tissue by the light. That is called tissue optics. So there will be, when light is going to fall, I am talking about the optical biopsy using fluorescence spectroscopy. Incident light fall, fluorescence. So definitely it is going to split into the different colors. Now incident light, if it is of the small wavelength, then emitted light will be of higher wavelength, and that higher wavelength we can measure. Now for and other thing is also there, transmitted light or scattering of light, absorption. So if any change, and that is the signature, means if it is a normal tissue, then these all fluorescence, transmitted, scattered light with a diseased tissue is going to be different. So with it is a non-invasive diagnostic tool in medical sciences, we are using the laser. In my starting of the lecture, the applications I have explained that in medical surgery laser is used. So here laser is of one single wavelength. Its intensity is high. We can bombard it and then emission, scattering, absorption, we can measure it by the spectroscopic tools. We can detect early stages of disease, particular in tumor. If the size of a nucleus is increasing, then there will be change in elastic scattering. If there is metabolic activity is increasing, then that will give you the biological, biochemical changes. Increases in concentration of related biomolecules, bond breaking, cross links are the signature of some disease, and that can be get from the fluorescence yield change, means there will be the fluorescence yield change will be there, and that is the signature. If there are the bond changes, then Raman scattering changes, and it is a signature of bond changes. If there is the change in blood concentration, then absorption change is the signature of the blood concentration changes, and in this manner we can able to detect early stages of the disease, and then it can be cured if detected early. Thank you for listening me patiently.